I appreciate that. Okay, so taking a moment to copy this example down. And incidentally, any of you let me know if you have any, let me know if you have any questions about your grade, okay? And of course, Michael will chat after class, no problem, okay? All right, so I'm going to let you copy this
Professor,
down.
just checked and you adjusted. It's
Yes,
all
it
good
is
now.
adjusted. And it should
Thank
be
you.
a little higher, Michael. It should be.
Yeah.
All right, good. Excellent. All right, let me give you a moment to copy this example down. Okay, and I'll just mention real quick, just a reminder now, the homework assignments, the extension, the late extensions, of course you have one due this Thursday. The late extensions for all the homework assignments, the most recent ones since the first exam, the extension should last until this Friday at 10:45 a.m. Okay, so all of the most recent assignments since the last exam should last until then. Okay, all right. So let us talk here now. We have here a tsunami, a model, a differential equation for a tsunami, and we know a tsunami is a huge wave that's created by, like for instance, magma disturbance under the earth, like earthquake type of thing. It creates a huge wave, and the wave, it gets created in the like middle of the ocean, but then it moves to the shore, right? And many people have died with tsunamis. They are and Zachary, we'll get to that question. We'll get to it, but one moment here. Let me finish this problem, and then I'll make a note of it. And all right, so here we have the differential equation where W, which is a function of x, is the height of the wave expressed as a function of its position relative to a point offshore. Andrea says she used to be scared of the ocean for this exact reason. Yes, I mean, I believe in Japan they have like warnings, like sirens, but I'm not sure how much time you have to get away, from the beach, But what we want to do is solve this differential equation, and we're going to use MATLAB to help us. So may I go to the next page?
Yes.
All right. So, okay, thank you, Thomas. Thank you, everybody. So, okay, here's the differential equation We, of course, will separate the variables. We'll separate the variables, and it's a separable differential equation. And then we'll integrate both sides. Okay, and here's the thing that is a little bit is difficult. This left-hand side of the differential equation is the antiderivative. It's not something you would know offhand. It's something that most students have not seen in like Calculus 2 at certainly Montgomery College. But there is an antiderivative of that, and we're going to use MATLAB to integrate it. Okay, so these are the commands. There are two commands that you need. Okay, first you have to define your sims w. So w is the variable you're integrating with respect to, and then you use the int command for integration. Now, normally we do our integration by hand. We use our techniques, you know, partial fractions, integration by parts, substitution. But this problem here, we really do need MATLAB to help us.
Wait, is sims w just like a formatting thing? So you just typed it in first?
Good question, Matthew. Sims w tells MATLAB, I want you to symbolically define the variable w. Because the answer, the antiderivative, is going to be in terms of w. So it stands for defining w symbolically. That's what that means. And anytime you do integration, at least the way I do it, I always use sims w or whatever the variable is, and then we have the integration command. So here's the integrand. This is the integrand here. And we're integrating with respect to w. Okay, and if you do that, you should get, then MATLAB should give you this antiderivative. Okay, and actually, let me just look at one thing here. One moment. One moment here. One moment, class. What I'm doing is I'm putting the command in MATLAB. Okay, I'm putting the command in MATLAB. And of course, invalid expression. So what's it get me on here? All right. Well, this should work. It should work. It's just the command should work. So just try it, and you should get this result because I did it previously. So okay. Now, what is this? What is this thing here? What is this? What is this? This is the TANH. That's called your hyperbolic tangent function. Okay, now you've heard of the tangent function, but some of you have not heard of the hyperbolic tangent. So the antiderivative of 1 over w times square root of 4 minus 2w is equal to negative the inverse hyperbolic tangent function of the square root of 2 times 2 square root of 2 minus w over 2. that's going to equal x plus c. Now I'm going to show you in terms of exponential functions how the hyperbolic tangent function is defined. But you know, this is what you'll get. And what I'm going to do, I'm going to multiply through by -1 both sides so that I get this result right here. Okay. Okay, are there any questions so far?
Yeah, Professor, you said you multiplied by what?
Yes, what I multiply by this equation here. I multiply both sides of the equation by -1. So negative times this negative here gives you the positive. So I have the positive inverse hyperbolic tangent of square root of 4 minus 2w divided by 2 equals -x plus c.
Oh, okay. Okay, thank you.
Okay, you're welcome. Are there any other questions? Okay, so now, well, we want to solve for w. So I don't want the inverse hyperbolic tangent function there. So I'm going to have to do something with that. But let's go to the next page. And of course, it's essential because like, for instance, the Webb-assigned problem involved a graph. It's essential to know how the hyperbolic tangent function is defined. Okay, how is the hyperbolic tangent function? Okay, how is it defined? Well, just like tangent is sine over cosine, the hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Okay, that's how it's defined. And the hyperbolic sine is equal, by definition, the fraction e to the x power minus e to the -x power divided by 2. And then the hyperbolic cosine function is, by definition, the fraction e to the x plus e to the -x divided by 2. Okay, so this is just to, you know, so really the hyperbolic tangent function, as well as the other hyperbolic functions, are in terms of exponential functions. They're defined, you know, this way. Now, so remember, this is what we had. We had the inverse hyperbolic tangent function of square root of 4 minus 2w over 2 equals -x minus c. Well, to remove the inverse hyperbolic tangent function, I'm going to take the tangent of that. I'm going to do it. I'm going to do the composition of the inverse hyperbolic tangent with the hyperbolic tangent, and then that will make them go away. How many remember compositions of inverse functions in maybe pre-calculus?
Yeah.
Yeah, that's right, Justin. And you know, here you go. Here's an
question.
example where you see it.
Professor?
Okay, no problem. There's a saying: when you take a math course, you relearn the courses you had before. Question.
Yes. Why is it that they don't tell us? Why aren't we told about hyperbolic, tan, sine, cosine in the previous calculus courses?
That is a good question, Andrea. I do not know why. Because when I took calculus, I learned about it. Like in the Montgomery College, the Stewart textbook doesn't really have exercises involving it, but it's nevertheless important. And so, well, you're learning about it now. Good question, Andrea. All right, now what I do here is the negative x minus c, I factor out a -1 and write negative x minus c as negative the quantity x plus c. And that's helpful because the hyperbolic tangent function is an odd function. In other words, if you were to graph that function, you would see it's an odd function, meaning that f of negative x equals negative f of x. And so that means that the negative of x plus c can, well, no, that means that I can rewrite the right-hand side, the hyperbolic tangent of negative of x plus c. I can write that as negative hyperbolic tangent function of positive x plus c. And that's helpful. That's helpful. All right. Now, of course, we still have to solve this equation for w. We want to, you know, what is wx? What is wx equal to? So we have to solve this. What should we do to both sides of this equation? That's right, Zachary. We should square both sides so we can remove the square root on the left. All right. So if I may go to the next page then, I'll show you that step. Wait, am I not recording here? Hold on. All right.
You are recording.
Am I recording? Okay. I don't see my little. I am recording?
We see the icon.
Okay.
Yes, sir.
Okay. I don't see my little red. I don't see my little red light up in the corner there. But oh wait, connection. Hold on. All right, so we're good, right, everybody? We're good. All right, so we need to square both sides of this equation, and that's what we're going to do on the next page. So just a refresher, you know, we started here. Okay, we used MATLAB to help us integrate. Now we're here at this stage. We have to square both sides of the equation, which we do right here. All right, let me give you a moment to copy that down, and then I'll talk about it. Zachary says, why did we not multiply the 2 first? Well, I have to square it. The 2 gets squared here. I'm squaring the entire left side. All right. Okay, I'll give you a moment to copy here. Okay.
Professor, so what happened in the bottom is that an identity? A trig identity? What it is applied on the,
Yes, actually, let's talk about that. So I do, basic algebra here. All right, and then, okay, what's going on here? 1 minus the hyperbolic tangent squared of x plus c actually is equal to the secant squared, the hyperbolic secant squared of x plus c. So you learn, for instance, one moment. So you learn, for instance, the identity that tangent squared plus 1 is secant squared. And therefore, yeah, okay, so this is a little different, isn't it? This is a little different. Tangent squared plus 1 is secant squared. But 1 minus the hyperbolic tangent squared is equal to hyperbolic secant squared. Okay, and and I'm replacing that. Right, that's right, Michael. That's right, Michael. You can prove the identity. Again, it goes back ultimately to, the definitions of, once we know the hyperbolic sine and hyperbolic cosine, we know the rest of the hyperbolic functions, how they're defined, because it's similar to the way our regular trig functions are defined. But this is, in fact, the identity. And so now W will equal 2 times hyperbolic secant squared of x plus c. And this, in fact, in WebAssign, this is what your answer should be when they want you to solve for W of x. In other words, that's the solution. That's the general solution to the differential equation. And that you type that exactly in the box for that fourth question in section 3.2, the assignment that was due Sunday, and you'll get the right answer. Okay. And again, I'll make sure you get full credit on that problem if because you'll have it'll give you a little deduction, right? But I'll make sure you're made whole on that problem. Now, also, we're given an initial condition that when you are W0 equals 2, that means, let me see here. Let me just see here. So, all right, with that initial condition, we want to solve for the constant c. Okay, we want to solve for the constant c. Okay, and so may I go to the next page? Are we good so far?
Professor, I realized that when I enter the answer in terms of hyperbolic tangents or even convert that to exponentials, it didn't work in WebAssign
Yeah.
until I placed that second squared answer.
Yeah, it only will take this answer here. This is what you're going to type into WebAssign. Exactly that answer. That's what it wants. So try that, Michael, and it'll work. It'll work.
Yeah, I already did it.
Excellent, excellent. It's because it's prettier. It's pretty. It's a pretty little answer,
Okay.
But now we got to solve for the constant c. So, okay, I'm gonna 2 is equal to 2 times the hyperbolic secant squared of 0 plus c. Okay, so that means 2 equals 2 times the hyperbolic secant squared of c, right? And I got to solve for c. Well, I'm going to divide by 2 both sides, and hyperbolic secant squared is equal to 1 over the hyperbolic cosine squared. And so hyperbolic cosine squared of c equals 1. And here's now where I bring in the initial condition. Okay, the initial condition, of course. Well, no, I am using the initial condition, but here's where I bring in the definition. So the hyperbolic cosine is defined as e to the x plus e to the negative x, all divided by 2. Right? That's how the hyperbolic cosine is defined. And so, you know, of course, I have my constants here. I have my c's. And this is not a function that you can solve. You have to solve this function graphically. But if you solve it, well, first of all, see, if you just say by observation, you know, sometimes we just solve things by observation. If c equals 0, then this equation is satisfied. But if you graph this hyperbolic cosine function, you'll see that c equals 0 would be the only solution to this. So there you go. That means when x equals 0, if w equals 2 when x equals 0, okay, if that's the height of your wave, 0 meters relative to a point offshore, then wx is simply equal to 2 times the hyperbolic cosine squared. Now, on that problem in WebAssign, they also asked for a graph. Well, to graph it, your calculator doesn't have like a TI-84 calculator. I'm looking at it. I don't see a hyperbolic sine or cosine on there. But no problem. Just replace, you know, hyperbolic secant is 1 over hyperbolic cosine. And let me see here. So I take the hyperbolic cosine and take the reciprocal of it, and then square it, and you can graph this. And I actually graphed it, and you know, it works out just fine. It agrees with the answer, and you'll see it looks like a wave. It looks like a wave, or something resembling a wave. And when I, you know, saw the graph, I said to myself, yeah, I can see why they use that differential equation to model a tsunami. And Wx represents the shape of the wave. Wx is the shape of the wave. The differential equation, dw dx, well, you know, how do they get that? That's a good question. Do they get that empirically through data, through observation? You know, it's not like a tank problem, you know, where you have rate in minus rate out. Somehow they got that original differential equation in, but w of x is this is what's going to look like a wave. That right here, this will look like, you'll see it. It looks like there's a big wave in the center, and then it falls off as you go further away from the center. All right, Ann, is that okay? You're welcome. Good question. Good question. All right, now, are there Well, are there any other good questions on this problem?
Yes, so you said we can graph this on MATLAB?
Well,
That-
this you could just type it in your TI-83 or 84 calculator. I mean, this is what you would type because your calculator understands exponential functions. So you could just type this in, Thomas, right here, and you'll get the answer. Your graph will look like one of the 4 graphs that they show you.
Oh, okay, I see it now. Thank you.
Sure, no problem. Are there any other good questions? All right, let me stop the recording.